Greetings and good evening, minions. I hope you're having a great day. I know I am, because we're about to do a little bit of chemistry, and what could possibly be more fun than that? As always, my name is Nathan. I am a PhD student in chemistry, coming up to the end of my degree, and I have realized that I am a big enough nerd that I enjoy echo, lots of echo. I don't know how to fix that. Let's see. I wonder if it's this. How's that? Is this still pretty echoey? All right. Do. Good now? Okay. Yeah. It for reasons that are not clear to me, there's two separate inputs for microphone and video capture device. So both of those being on seem to cause some issues. Anyways, yeah. Terribly odd. No matter. Yeah, so it was really lovely. Last week, Twitch discontinued support for the Twitch Studio streaming software, and so I had to find a new program, and this is my first day with it. And yeah, so this is the first kink has been worked out. So lovely. I'm sure there will be more to come. At any rate, as I was saying, I do chemistry. I get paid to do chemistry, which is kind of nice. And I'm a big enough nerd that even when I'm not being paid to do it, I'll still talk about it, because that is just kind of fun for me. Anyways, all right. So let's see if I can find the buttons that I need. I think we'll just go over here, and there we are. Okay. So, last day, we were talking a bit about orbitals, and so we'd gotten to talking about not just orbitals, but how we put orbitals together. So when we go from atomic orbitals to molecular orbitals. And this is generally the easiest to visualize using this linear combination of atomic orbitals kind of procedure. It's kind of like what I've gotten written out there, wherein the atomic orbitals that we assign to the individual atoms are combined into molecular orbitals. And when we do that, the number of atomic orbitals must always equal the number of molecular orbitals. So when we have two orbitals interacting, there is always there's always two ways that they can interact, which is to have an all-in phase interaction, wherein the energy of the molecular orbital is lower than the energy of each of the individual atomic orbitals, and there is an out-of-phase interaction where the energy of that orbital is higher compared to the atomic orbitals. And so there's a stabilized interaction, which is in phase, and a destabilized interaction, which is out of phase. And so by counting up the number of electrons in each of these molecular orbitals, then we can get a sense for the bond order between those individual atoms that we're comparing. So in the simplest case of two hydrogen atoms, we have one electron coming from each hydrogen, because that's what they have when they are neutral. And so those combine into the molecular orbital, this sigma orbital, called sigma because it has electron density on the axis between the two atoms. And we put them both of the electrons in this molecular orbital because of the Aufbau principle, which says that when we're populating electrons in the ground state, we do so by filling the lowest energy orbitals first. So with just 2 electrons, they both go here, and then we can calculate what's called the bond order. And this is more or less just a measure of like how strong is the bond between these 2 atoms. And so that is taken by the number of electrons in bonding orbitals minus the number of electrons in antibonding orbitals, which in this case is 2 minus 0 divided by 2. And then that equals 1, because we expect a single bond between 2 hydrogen atoms, which is good, because that's all they can sustain anyways. They can't have more than that, because that would be breaking some rules. Yeah, so the distinction between bonding and antibonding. When you have an in-phase interaction and you have so these 2 atomic orbitals overlapping, then the analogy I like to use is if you have 2 bubbles floating around and they find each other, they'll up into one bigger bubble, and that's kind of what happens with these in-phase interactions. Is it will have continuous electron density between these 2 atoms, and that is a bonding interaction that holds these 2 atoms together. Antibonding interactions will have a node between the 2 atoms. So it says perpendicular to the axis between them, and a node is just a line or a plane of 0 electron density. So there's these 2 out of phase orbitals cannot overlap, cannot directly interact. They can push up against each other like a couple of balloons, but they can never combine like the in-phase ones do. And so this is a disruptive force. These actually want to get away from each other, so by populating antibonding orbitals, you reduce the bond order between the 2 atoms. And this can kind of be seen in just the distribution of these orbitals. So we have the atomic orbitals here on kind of along this line, and the bonding interaction is stabilized. And so when these 2 hydrogen atoms come together, it is more energetically favorable for these 2 to form this molecular orbital that we see here and populate that with their electrons, which also has the effect of holding these atoms together. And that is a more energetically favorable situation than these 2 atoms existing individually with 1 electron. And then if we give these hydrogens extra electrons, so we basically have an H minus as 2 electrons each, now we have a case where we still must have 2 molecular orbitals because we started with 2 atomic orbitals. But in this case, we have 4 electrons, so we populate the bonding orbital and then we populate the antibonding orbital. And when we do that, we come out to a bond order rather of 0. And so in this case, whatever beneficial interaction you get from this in-phase interaction is completely canceled out by the raising in energy by the energetically unfavorable situation of populating this antibonding orbital. Because when you populate antibonding orbitals with electrons, you break bonds. And this is something that is carried through into a lot of synthetic chemistry later down the road. But we're trying to keep to simple situations. But yeah, so this is a way that we can just kind of have a quick basically a prediction, I guess, of these interactions between these two atoms. Well, I shouldn't really call it a prediction, I suppose. That's not exactly the right word to be using here. Description, I suppose, would be a little more accurate. So yeah, and then I just threw up this little drawing here. This is just of a neutral helium. And helium, of course, is in the top right. It's the second element in the first row, which only has a 1s orbital accessible. And so helium comes with 2 electrons each, and so they have exactly the same bonding situation as an H minus here, which is called an isoelectronic. Well, I guess helium and H minus are isoelectronic. There we go. That's how you say that properly. And so because of that, the bonding and antibonding modes of helium, the molecular orbitals, are always going to be filled when you have a neutral helium. And this is why we do not find helium in little bonded pairs like we do hydrogen or nitrogen or oxygen or fluorine or chlorine or all these different things that like to be these diatomic compounds. Helium just likes to be a solitary atom of helium. It will not bond with another helium atom or really with anything else because we'll immediately have this bond order going to 0. And that's why they're called noble gases, because things like helium, neon, argon, krypton, these all have a very strong preference to exist as these monoatomic elements. And molecular orbital theory is a really handy, really simple way to explain why that is. So the other thing that I was talking about a bit was identifying nucleophilic and electrophilic sites on different molecules. And just very briefly about that, nucleophilic sites on a molecule are going to be a spot where you have a high electron density. So it's going to be an atom with a lot of lone pairs, or an atom that carries a negative charge. Those are what we mean by kind of like higher than normal electron densities. And electrophilic centers are going to be the opposite. They're going to be regions of a molecule that have a deficiency of electron density in some manner. These are going to be the lower electronegativity end of a polar bond, such as a carbon to oxygen bond. Or they're going to be sites that have a positive charge like that one there. I'm not going to talk terribly much more about that because I want to keep going on and do some other stuff. Have a big yawn. Don't mind me. Okay, so this one. Oh yeah, I'm skipping over this section because the question that's being asked is identify which arrow pushing pattern is utilized in the following reactions. I don't know what the hell they mean by that. That is not clear to me. So let's not worry about it. So we'll go on to the next one. So draw curved arrows to accomplish the following transformations. It may help to draw in the lone pairs. I object. You should always draw in the lone pairs because we're good little chemists. And that's some big dots. Let's make smaller dots. Okay. Do. Okay. So, right off the bat, this one, to me, So this is just a simple exchange of this bromine atom for a chlorine atom. And all we've got here is a Cl minus, a chloride anion. And as I just said, things that are nucleophilic tend to have a lot of lone pairs around them, and or a minus charge, which this chloride has all of. And so that is fairly clearly going to be our nucleophile. And in the starting material here, we've got a carbon attached to a bromine. Bromine is more electronegative by a certain amount that I don't remember off the top of my head because I could just Google that, but I don't need to. So, so this carbon has a little partial positive charge here, and the bromine has a partial negative charge because they are part of a polar bond, a bond in which the atoms on either end of the bond have significantly different electronegativity. And bromine being the more electronegative, it is going to be pulling harder on the electrons in the bond, and kind of gathering those electrons to itself, giving it kind of this small excess of electron density. So we have a little delta minus for the bromine, delta plus for the carbon, and that makes the carbon here an electrophilic site. And so when we have a reaction happening here, we're going to have one of the lone pairs from the chlorine is going to come up and around and attack that carbon. And so this arrow going from a lone pair and pointing directly at an atom is indicative that we are forming a new bond. So we form a bond between the chlorine and the carbon here. But when we do that, now this carbon, excuse me. So this carbon had a hydrogen that just was not drawn because it is implicit in a line structure. But it is there, and we have to keep in mind that it's there because that kind of matters. So when we're talking about carbon or any of the second row elements, like what would it be? Boron, carbon, nitrogen, oxygen, fluorine, so on and so forth. I don't know why I said so on and so forth. That's just kind of it. So the second row elements cannot have more than 8 electrons around them. They cannot exceed that octet. And when there's 2 electrons in each bond, that means that it can have a maximum of 4 bonds at a time. So here we're trying to we're forming a 5th bond with that carbon, which means that one of the bonds must break. Because we cannot have more than 4 bonds at any time. So something's got to go. Okay, I'm just going to take that out. So we got forming a new bond with the carbon here. Now, there's the way that we go about choosing which of these bonds to break is we look at the products and we say which of these is the least bad. So let's say, for argument's sake, that we break this bond, which that was a terrible arrow. You'd think after 12 years I could draw a decent arrow. You'd be wrong. Okay, so let's break this bond. So we're breaking that carbon-carbon bond here. So if we do that, I'm not going to worry about all this other stuff that we form, but I want to look at the fragment that we're kicking off in order to accommodate that chlorine. Because this is how we decide what's the least bad thing to kick off. So if we kick this off, what we end up with is, so we got CH3 down here, that's this one. This is a CH2, with a lone pair and a negative charge. So, if this looks terrible to you, good. It should. This is terrible. We do not like to put lone pairs and indeed a negative charge on a carbon, because a carbon is not a particularly electronegative element, so it does not like to have a lot of excess electron density. And it is a carbon anion, or a carbanion, is something that is extremely reactive. And when I say extremely reactive, the other side of that coin is it means it is not stable. And this is because this is a first of all a highly focused charge. This negative charge is fully localized on the carbon, and as one of my professors loved to say, nature abhors a focused charge. And so when this carbon has essentially extra electrons on it, then it's going to be a highly focused negative charge on an atom that is not particularly well equipped to carry a negative charge because of the electronegativity of carbon. And so what that means is that this carbon is not pulling very hard on its valence electrons, and we've just put a bunch of extra electrons in its valence shell. And so those, let's just keep the quotes on, quote unquote, extra electrons are going to be held very, very loosely by the protons in carbon's nucleus. And so those are going to really easily react with other things, which is why it's reactive, which is why it's not stable. And when you're looking at these options and you have the option to create something like this, a negative charge on carbon, has no other stabilizing factors on it, like the hydrogens here are not helping out whatsoever, because carbon is in fact more electronegative than hydrogen. And so it's going to already have a very small partial negative charge, and this just makes it worse. So this is all around just terrible, and it is sufficiently bad that we would say this will not happen. Another thing that you could call this, like anything that you break off of this carbon chain, would be called a leaving group. And this is an exceptionally bad leaving group. And it is such a bad leaving group, it is so energetically unfavorable for this to form that it just won't. If you think you've kicked out a carbanion that has no stabilization whatsoever, you haven't. You are incorrect. So this, kicking out this group here, does not happen. Cannot happen. So our other options are the hydrogen, which, if we did that, we would have an H minus. This is also extremely bad. Hydrides, we can make them if we introduce some really harsh reagents. They make very, very strong bases and good nucleophiles. But essentially, this is a bad option. An H minus is a terrible leaving group that you would only invoke under the most extreme of circumstances. And this is not the most extreme of circumstances. So let's just not do that. Now, the third option would be kicking out this methyl group here. But if you did that, you'd essentially have the same situation as this. You'd be kicking out a carbanion, and that's terrible. Please don't. Just don't. So for the same reasons as down here, we are not going to break that bond. Now, if we were instead to break the carbon-bromine bond, now we've got, well, first of all, we've got this, our intended product. But the other thing that we have as a product of this reaction is a bromide anion. And a bromide anion, relatively speaking, is very stable. And it is stable because, first of all, bromine has a high electronegativity. So its protons in the nucleus are pulling like significantly hard on its outer electron shells, and that makes it a somewhat better anion. Certainly a far better anion than carbon, just from that. But also, the other really important thing in stabilizing these charges is the size of the atom. And bromine is a, let's see, fluorine is 2 bromine. So bromine is in the fourth row. And so it's a very large atom. It has multiple shells of electrons underneath the valence shell, and so its valence electrons, which are these ones that we're talking about with the octet here, are they're in a very large shell around the bromine. And what this means is that the negative charge on a bromine is much more spread out than it would be on, for example, a carbon. Okay, so let's I'm going to illustrate this a bit. But yeah, and if you remember, like the saying that nature abhors a focused charge, well, sorry, my brain stopped for a second. When we're talking about a focused charge, we mean a charge that is confined to a small volume or area, however you like to say it. So with a carbon anion, this negative charge is in quite a small volume, whereas in bromine, these are absolutely to scale, and you should take this as completely true. Just kidding, please. I mean, just don't take much that I say too very seriously. It's generally not a good call. Okay, so let's say these 4 little negative signs are the negative charge, and so in the carbon they're relatively close to each other. But in the bromine, these ticks are much farther apart. It's the same charge either way. It's a -1 charge. But in a bromine atom, they're far more spread out than in a carbon. And so because the charge is more spread out, it's less bad. It's less reactive. It's more stable. It is energetically preferable. So, because like I keep saying, like 98% of all chemistry is just reducing electron repulsion, and that's what this does. Because when these electrons are farther apart, they repel each other less. Okay. So let's take that away. Cheesiest of Cakes, it's lovely to see you. I hope you had a great weekend. Not to worry at all. I appreciate you showing up, and happy Tuesday indeed. Alrighty. Okay. So yeah, just to catch you up, Cheesiest of Cakes, we're just going over, just drawing mechanistic arrows to accomplish the following transformations. And so in this one, I've already marked that up mark that up to hell. So let's just start with the next one. So we've got this tert-butyl bromine. This is just a T-butyl group attached to a bromine. I can draw, really. And so the product here is just exactly the same thing, just without a bromine. And so the only arrow that makes sense here is one that goes from the carbon-bromine bond to pointing at the bromine. And what this implies is that we've taken the electrons from that carbon-bromine bond, and we break the bond and put the electrons on bromine. And we do this because when we break this bond, the electrons go to the more electronegative element, which is the bromine here. And so this one arrow leads directly to these products. So that one was fairly easy. There is a second step here, which has a chloride. Drawing all its lone pairs. So to get this, we just have just an arrow from the lone pair of the chloride to that carbon, and this is a positively charged carbon, which is called a carbocation. And so this is a carbon with 6 electrons around it. It is electron deficient, it has a positive charge, and it would very much like to have some more electrons on it. And remember when I was talking about electrophiles, they tend to have a positive charge because they have a region of reduced electron density. That's it. The carbocation is an electrophile. It is a very, very strong electrophile. And so it's looking for electrons from more or less wherever. And this chloride is around and just reacts by forming a bond between the chloride and the carbon. And in this case we do not have to break any of the other bonds because this carbon only has 6 electrons around it, 3 bonds, and carbons always want 4 bonds around them. Okay. Okay. So, for this one, we're going to draw lone pairs because we always draw lone pairs because we are good little chemists, and we would be remiss to not. So, now, when you're approaching these mechanistic questions, really the first thing to do is to look at the starting materials and the products and look at like what has changed between these two molecules. And so in this case, what's changed is all of the stuff around here. These 3 carbons have not changed. Let's leave those alone. But here we've got an alkene, a carbon-carbon double bond. That is not there in the starting material. We also do not have the iodine, and, well, we may or may not have hydrogen. So one thing that will help is generally going to pretty much always be helpful is to draw out all of the atoms around a reaction site. Let's stick that out. That's a very long bond, but that's fine. Okay. So yeah, especially when you're given line structures where hydrogens attached to carbons are generally taken to be implicit, which means you got to put them in yourself or just keep in mind that they're there. But especially when you're starting out in chemistry, that is much easier said than done, and it is very easy to get off track, or to get just to forget that that the hydrogens exist, and occasionally they matter. So when we draw all of these out, we see that this carbon, in fact, is attached to two hydrogens. This carbon is attached to an iodine and a hydrogen. Now in the product, we've got just one hydrogen on each, because again, every carbon can only support 4 bonds at a time. So 1, 2, 3, 4. Because the alkene, the double bond, counts as 2 bonds. So now what's happening here? So what we've got is we've got tert butoxide, T-butoxide, which is a very strong base. And generally, when you're given a mechanism that has a strong base, or a strong acid, or just something really reactive like one of those, typically you look for a place to use it. So what do bases like to do? Bases like to pull hydrogens off of stuff, and there's a couple of good options here. And just from looking at the starting material and the products, we can see probably the best candidate is the hydrogen that was drawn in here, because we need to have a hydrogen on each of these carbons when we're done, and so removing this hydrogen would be a pretty quick way to get there. So let's start by using the base as a base. And so that is always, you go from the source of the electrons to the target, which is always going to be the base to the acid. So this oxygen forms a bond with hydrogen, but hydrogen can only support 1 bond at a time. And so the hydrogen carbon bond has to break. Because this hydrogen can only be attached to one thing at a time, and we're putting it onto the oxygen now. So these electrons have to go somewhere, and there's 2 ways to do this. There's the extra long way that is genuinely not correct, because this does not happen in a stepwise fashion. All of this stuff happens at once, and so I'm just going to draw out the stuff that actually happens. So this bond breaks and moves, the electrons move over here to form a double bond. So we indicate that by, we have the base of the arrow on the carbon-hydrogen bond. That means that this bond breaks, and then the electrons are pointing directly at the bond between these carbons, which means that we're forming a multiple bond, forming a double bond from the single bond here. So when we do that, now this carbon, this carbon here, this is already attached to 4 things. This already has 4 bonds, 1 here, 1 here, 1 here, 1 here. And so we're trying to form a 5th bond to it, which of course we cannot do. We can never have 5 bonds to a carbon. And this is another one of my professors like to say that there's 3 certainties in life: death, taxes, and 4 bonds to carbon. There's exceptions to this, of course, as there is to everything, but generally pretty good rule of thumb. So we have to break one of these bonds, and just exactly the same as we did up here, we can go through each of the possibilities of the bonds that we can break, and then assess them based on how stable the anions are that are produced. But I don't think we need to do that, because we gave that a pretty thorough treatment already. So we're just going to skip to iodine. Is a significantly electronegative atom here, and it is the one that if we kick it out and form I minus, because of the size of the iodine atom, which I have conveniently hidden behind my face, because of the size of the iodine atom, the negative charge is very, very spread out, even more so than for a bromide. So this is a very stable anion, and so we're pretty okay with that carrying the negative charge here. Yeah, and that produces our intended product here, right? Because the hydrogen ends up attached to that oxygen. We end up with the double bond between the carbons here, and one hydrogen on each side, and then the iodine just hanging out, being a little guy. Okay. Is that all of them? Ha, sure was. Okay. Okay. Alright, so the next question deals with predicting carbocation rearrangements. And so carbocation rearrangements are, they can be invoked in pretty much any kind of synthetic mechanisms, but the most common context in which you'll find carbocation rearrangements is in SN1 reactions. So I'm just very, very quickly going to provide like a bit of a schematic for SN1 reactions. So we'll have a carbon that is attached to something. This X represents just like some leaving group, which is an atom or a fragment that is more electronegative than the carbon, and can serve as a decent leaving group. So we've got things like bromine, iodine, or chlorine, pretty much any of those halogens except for fluorine. Because fluorine, if you make an anion out of it, it's very, very highly electronegative. It's the most electronegative element on the table, but it is very, very small. And so that charge is very highly focused. And so while this is a thing that can exist, like we have, fluoride salts, like sodium fluoride in our toothpaste. One moment, I need to see. I am back. I am alive. We're okay here. We're all okay here. Situation normal. How are you? Okay. So, fluoride is very electronegative, but very, very small, which makes it not a good leaving group. Not a great anion. Like I said, it exists, but when it's in a carbon-fluorine bond, a fluorine is very difficult to detach, which is actually has tons of uses in things like non-stick coatings, where we have things like things like Teflon are these alkanes with that are fluorinated. So they have carbon-fluorine bonds instead of carbon-hydrogen bonds, because it's much harder to break a carbon-fluorine bond. One of the strongest bonds on the table. Not the strongest, but one of them. So we have things like perfluorooctanoic acid, and we've got a huge number of different, like Teflon is a trade name, but they're all like these fluorinated alkanes, often with functional groups. But anyways, also though very, very useful in pharmaceuticals for making these really, really stable groups. and so that these fluorinated carbons tend to pass through like cell walls and membranes much easier. Anyways, that is really neither here nor there, but it is an interesting thing. I mean, you should talk about that sometime when I've had a bit of time to look it up. Also, everybody say hello, Daphne, because she is lovely and has paid us a visit in order to get some water. Strategically placed? Yes, I think so. So, other things that can be good leaving groups. Things like... Oh, why is my brain blanking? Can have things like if there's a... if you have a protonated oxygen, that is a phenomenal leaving group, because if you break a carbon-oxygen bond here and put the electrons onto the oxygen, what you've got is just neutral water, and that is very, very stable. Because this is one of the main ways that we assess the quality of a leaving group is like by asking like how stable is the product here. So yeah, if you have a protonated OH2 group, your leaving group is water, and that's phenomenal. There's lots of other choices. There's things like O2. CH. These sulfonate esters. I'm not going to get terribly much into what those are, but it's all I can think of right now. Although there's many more, because people have written volumes about these things. I just don't have them in my brain right now. That's okay. So in an SN1 reaction, we have a carbon hooked up to a leaving group of some sort, and then in the first step of SN1, the leaving group just leaves. This group takes its electrons with it, and that produces the carbocation. So let's just put the hydrogen in there for completeness. So the first step of SN1 produces a carbocation on the carbon that was attached to the leaving group, and then we have some kind of nucleophile, basically just anything with some electrons that it can share, will come around and attack the carbocation, and that just produces that just attaches the nucleophile to that carbocation. Now, like I was saying, the carbocations can rearrange in order to form carbocations that are more stable, and this SN1 type mechanism is the place where you will most often see carbocation rearrangements invoked, and because when we're going through an SN1 reaction, the carbocation is highly reactive, and the ability of a molecule to do SN1 is dependent upon forming the most stable carbocation possible, because it's an extremely unstable thing. So the longer that you can make this carbocation exist, that gives more time for these things to tumble around in solution and encounter a nucleophile. Because remember, we're talking about like in a real world context, we're talking about molecules in solution at like relatively low concentrations. These are by orders of magnitude outweighed by like solvent molecules, and so the reactive bits, the carbocations and the nucleophiles, have to run into each other in solution. They have to just kind of come together and bump into each other at random. Luckily, there's enough of these that it happens fairly often, but essentially, in order to have this reaction, this carbocation needs to survive long enough so that a nucleophile, so that it can encounter a nucleophile. So, if you form a carbocation, and you can rearrange things to make that carbocation more stable, which is to say that just to get that carbocation to survive a bit longer, then it will rearrange in order to form something that's better. But there's two rules to carbocation rearrangements, and these are very, very strict rules, and they both have to be fulfilled in order for a carbocation rearrangement to happen. So, first rule, very, very important, is that you must be able to form the carbocation in the first place. Okay, so what do we mean by that? What I mean is that if you have, like if the carbocation that you would form in an SN1 reaction is not stabilized in some fashion, then it is simply too energetically expensive to form it, and you just won't. And so when we're talking about, so it's in this step. So things that stabilize carbocations are things that can redirect electron density towards the carbocation. Because when this carbocation forms, essentially this carbon gets much more electronegative. It starts to pull very, very hard on any electrons around it, mostly the ones in bonds. And so if you have a carbon that is only attached to hydrogens, don't worry, I'll move my big fat face in a second. Okay, so if the carbon is only surrounded by hydrogens, I don't know why I put that there, I don't need it. So like if you're trying to form this, if you had a bromine on here and it left, you'd be left with a CH3 plus, a carbocation, or a methyl carbocation essentially. And so this carbocation is completely unstabilized. This is as close to zero stabilization as it is possible to get, because the hydrogens only have one electron, and that is part of the carbon-hydrogen bond. And so there is no extra electron density for this carbon to pull on. And so there's no stabilization here. If you have something like this, there we go. So if your carbon is attached to another carbon, so that's just saying this is like a methyl carbocation, then this carbon has more electrons. It has core electrons, it has electrons that are tied up in its carbon-hydrogen bonds, so there's more stuff that this carbocation can pull on through the bonds and get like just a little bit, just a smidgen of extra electron density. So there's a very small partial negative charge to offset this full positive charge. And this is this would be called a primary carbocation because like primary, secondary, tertiary are generally referring to how many carbons is the atom of interest, in this case a carbon, attached to. So this carbon is attached to one carbon, so it's a primary or 1 degree carbocation. But this, so there's a tiny bit of stabilization here, but it's not much, and it is not enough to do SN1 with. And so you need to have more stabilization than that in order to form carbocations. So if we have a second carbon attached here, we have a secondary or a second degree carbocation, and yeah, gross. That's even worse. Okay, I can't draw it today. That's okay. There, that's nice. So now this has 2 carbon groups that it can pull on for some electron density, and so it gets a little bit larger of a partial negative charge to offset that full positive charge. It's still very, very positive. It's still an extremely good electrophile, but it is slightly stabilized by the presence of these methyl groups. And when you get to a secondary carbocation, now we start to be able to do SN1 reactions. It's not great. Secondary substrates, the carbon bearing the positive charge being the substrate, secondary substrates are like, you can marginally do this. Like they're slow, but they can happen because there is just enough stabilization to make it go. If you have something like this, so this is a tertiary carbocation, and now we're in business. Tertiary carbocations are quite stable. They're still very reactive. These are still phenomenal electrophiles, but they are sufficiently stabilized that it makes SN1 reactions not just possible but facile, which is to say that, like, yeah, it can do the chemistry. So the other the other situation that we can have is if we've got not 3, thank you. Okay. So, if we've got a carbocation that is adjacent to a pi bond, which say a more than single bond, a double bond or a triple bond, then we have resonance stabilization. So we can take the electrons from that double bond, break the double bond here, and move those electrons to form a double bond here. And what that does is so when we have this resonance structure, we are moving the carbocation from this carbon over to this carbon, and so that positive charge is shared by these 2 carbons. It's essentially cut in half, and so this one would be a primary because it's a carbon attached to one other carbon, but a primary allylic, which just indicates that there's a pi bond adjacent to it, which can delocalize that positive charge onto multiple atoms, and that is a perfectly good substrate to do SN1. Resonance stabilization is extremely powerful. It's a very strong stabilization for well, charges in general, but carbocations in this case. So this is to say, like, when we're assessing if we can do a carbocation rearrangement, we have to be able to form a carbocation in the first place. Primary carbons cannot form carbocations. Carbons that are like part of a pi system, so like not next to a pi bond, but part of a pi bond, cannot, under any circumstances. You cannot do SN1 with those. You will not form a carbocation for those because they are completely unstabilized. So you have to have like at least a secondary carbon substrate, or you need some kind of resonance stabilization. So that is the first rule, is you must be able to form the carbocation. And the second rule is that the rearrangement must improve the carbocation. So if we're going to rearrange a carbocation, you could go from secondary to a tertiary. That's fine. You could go from a secondary to a secondary with resonance stabilization, and that's absolutely fine, because both of those are big improvements. But you cannot go from a secondary, just a normal like secondary carbocation, to a secondary carbocation, because that's not an improvement. There's no motivation for the rearrangement to happen. So have to follow those two rules. You have to be able to form the carbocation, and you must improve the carbocation in order to have a rearrangement. And now let's talk about what rearrangements are. So in this one, so this is predict if the following carbocations will rearrange. Spoiler alert, this one does. So there is, again, a hidden hydrogen contained here, and we can move that. So if we break this carbon-hydrogen bond, and we're pointing directly at the carbocation. So what this is saying is that we're breaking the carbon-hydrogen bond and putting the electrons on the hydrogen. And so basically it's this H minus with a lone pair on it is coming and attacking this carbocation. And because this is essentially the group that we're moving, this rearrangement is called a hydride shift. And what this produces is this atom. So we've attached the hydrogen here, the H minus here, so formed a fourth bond to this carbon. So that's neutral now. That's not the carbocation anymore. The carbocation has moved to this carbon in the center here, and that is connected to 3 carbons. So while this one is a secondary carbocation because it's attached to 2 carbons, this one is a tertiary carbocation because it is attached to 1, 2, 3 carbons. And so for that reason, this one is absolutely fine. It follows both of the rules. We can form a carbocation on a secondary substrate, but a tertiary substrate is better. And so we do this fairly difficult, this fairly energetically expensive move. We can do that. So now in this case, we've got. I'll be a good little chemist and draw all the hydrogens there, as well as the one on here. Okay, so the carbocations here is the same as above, is a secondary carbocation. But now, if we were to move one of the hydrogens, have a hydride shift over to that carbocation, what we would produce is okay, so we've put an extra hydrogen there and moved the carbocation over to here. Oh, I wish I could draw. But now this carbon is also attached to just 2 carbon groups. And so this is also a secondary carbocation. It's not an improvement. And so this will not happen. So we cannot do that carbocation rearrangement because while we can form the carbocation, the hydride shift does not improve it. Okay. Alright, so this one again, we've got a secondary carbocation over here. I guess I'll draw these for completeness. So, while we could assess the option of, could use one of these hydrogens to do a hydride shift, we'd be moving the carbocation here, which is exactly the same as up here. It's not an improvement at all, so we're just going to not do that. Now, if we take one of these hydrogens, then what we produce is this molecule here. So, this is a secondary substrate. This is also a secondary substrate. However, these are not the same because there is a pi bond that is one bond away, so we can, in this case, we would break the pi bond and use the electrons to form a double bond between these carbons. And that is, in fact, a resonance structure because none of the connectivity has changed. So this produces okay. So this has relocated the double bond here and produced the carbocation on the terminal carbon here. But this is a resonance stabilization, right? Because these are resonance structures of one another. And so when we do this carbocation rearrangement, we do this hydride shift, we transform it from a secondary carbocation to a secondary carbocation with resonance, and that again hugely stabilizing and very powerful. So this is absolutely a carbocation rearrangement that would happen, and you would expect that like this would be a very favorable substrate. How can I say that without it being silly? That is a I don't have words anymore. My brain's getting fried. So, but it makes that carbocation much more stable, and that is what we want when we're talking about carbocation rearrangements. We're aiming to stabilize the um, stabilize the carbocations so that it can do its thing. Okay, so in this case, now we've got a secondary carbocation. But now, if we were to do a hydride shift from here, we'd move one of these hydrogens over to the carbocation, and the carbocation would be here. I may as well draw all of the hydrogens so as to not be really wrong. But if we were to do that, we would have a primary carbocation if we used these hydrogens here for a hydride shift. So that would be making this carbocation not just worse, but non-viable. So we're not going to do that. We're not going to use those hydrogens at all. And this carbon has no hydrogens on it. But what it does have is a methyl group, and we can, just like with a hydride shift, we can also do a methyl shift. It's a little bit harder, a little bit more energetically expensive, but it can absolutely happen, especially if it makes a carbocation somewhat less terrible. It certainly can happen. So if we take this entire methyl group and shift it over to that carbocation, what we produce so we've moved the carbocation here, and this is a tertiary site. So we've changed from a secondary carbocation into a tertiary. So the carbocation can form in the first place, and the rearrangement improves it. So both of the criteria are fulfilled. So that's just great. Now we can do the same thing here, where we move the methyl group over to the carbocation. And then that produces this molecule. Let's make that a little less obtrusive. Okay, so we form that from the methyl shift. But this one starts at a tertiary carbocation, and after the methyl shift, it is still a tertiary carbocation. So this will not happen because this has improved nothing. It is a sideways step, which is not good enough to do a carbocation rearrangement. Can't do it. All right. And this one, very quickly, just to finish up, has methyl groups that can shift. We put the carbocation over here, and it moves from a secondary to a tertiary. I'm not going to bother drawing all of this out because we've done it a few times at this point, and I trust you all to keep up. Okay, so that's all of that question. So again, carbocation rearrangements come down to two rules that absolutely must be strictly followed. You have to be able to form it in the first place, and the rearrangement has to improve the carbocation. If one of those criteria is not met, you're out of luck. There's no possibility of rearrangement. So even if you're really tempted, let's say, all right, I keep forgetting. I'm skipping ahead of stuff. So we got just an alkyl bromide, and let's just say that the bromine leaves behind a primary carbocation. Now, there are hydrogens here, that like if you formed this, you could do a hydride shift and move it into a secondary carbocation that could then go and do stuff. But you can't form this in the first place. You cannot form a primary carbocation unless it is resonance stabilized, and this one is not. There's no possibility for resonance here. So you can't do that carbocation rearrangement because there's no carbocation to rearrange. All right. So, well, with that, I do believe that I'm going to call it a night. Because my brain it's still working, but it's not working fast. So I'm going to call it here. I appreciate you hanging out, and I hope you have just a lovely evening. I will be back on Friday now that we got this the streaming software stuff figured out. So I hope I'll see you then, and I hope you have a lovely night, and okay, bye!